We saw in the last lecture that as the number of rectangles increased, went to infinity, the sum of their areas approached the exact area between the curve and the x-axis. This limit is called the definite integral. Here's the definition. So the limit of the Riemann sum is the definite integral, and it's denoted with this fancy S, a to b f of x dx, and it is the exact area between the curve and the x-axis. Counting area below the x-axis is negative. So a few comments on notation. This stands for sum, fancy S. dx is an infinitesimal small change in x. And thus f of x dx is the area of this infinitesimally thin rectangle located at x. Here's our picture here. So we have a, b, we have x somewhere in between. And the area of this rectangle is height f of x and width dx. So its area is f of x times dx. And so putting it all together, what this definite integral is saying is it's the sum of areas of these thin rectangles from A to B. Let's look at an example. So find the definite integral of 1 to 3, 2x dx, which is the area between 2x and the x-axis from x equals 1 to x equals 3, using the limit definition with the Riemann sum and geometry. And when we find definite integrals, we often use the word evaluate. So this, in the future, this might be phrased evaluate. Okay, so let's use the limit definition. So 1 to 3, 2x dx is going to be, so the limit as n goes to infinity, I equals 1 to n, f of a plus b minus a over n times I, b minus a over n. And now we just need to put in all the things that we know, the a and the b and the f. So the a is 1, the b minus a is 2, 3 minus 1 is 2. And then the f is 2x, so we'll just replace x with the interior of this function. And now we're ready to simplify and then take the limit. So distribute the 2 and the 2 over n, and we get 4 over n plus 8 over n squared times I. And then let's work this out. So this is a Riemann sum. We'll write it out as a sum in long form. So 4 over n plus 8 over n squared times 1 plus 4 over n plus 8 over n squared times 2. And then this just keeps going to 4 over n plus 8 over n times n. And now we're going to collect all the 4 over n's, so we'll have n of these 4 over n's, put them all together, and then we'll collect the 8 over n squareds times 1, 2, all the way up to n. So there's n of these, so it's going to be 4 over n times n. And then we're going to use the formula here. So 1 plus 2 plus all the way up to n is n times n plus 1 over 2. Almost done here. this is just 4, and this is, if you work it all out, it's going to be 4 plus 4 over n. And if we take the limit as n goes to infinity of this, we'll get 8. Because the 4 over n goes to 0, and the 4 plus 4 is 8. Okay, so that's how we do it using the limit definition. Now we're going to check our work by doing the same thing again with geometry. And we'll just draw a picture for this one. So we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. It's 2x, so when we put in 1 we get 2, we put in 2 we get 4, put in 3 we get 6. There's our line, and we're going from 1 to 3, so we're finding the area between this line and the x-axis. And if we just divide it up, we'll see that this area is 2, this area is 2, this area is 2, and then if you combine those two triangles we get area 2. So the total area, which is the definite integral, is 8. And next time we'll look at another way to evaluate these definite integrals using what's called the fundamental theorem of calculus.